Yeah,
Great.
awesome.
Okay, so I'm going to give a talk. It's relatively short, and it's mostly asking questions rather than telling you something about products or HPE. So it's a bit different than what you've seen me present before. I'm going to talk about ideas around navigating diverse architectures for weather and earth system modeling. As many of you know, I've worked both on the vendor side and the customer side. I started my career at Cray and then was SGI and then Cray and then SGI before leaving to go to the customer side and worked at Oak Ridge and NREL, and then came back to Cray in 2018. And we got acquired by HPE, so now I work at HPE with my former SGI colleagues, and it's all a lot of fun. And I'm looking at the Earth Sciences segment, so mostly weather and climate across the world. And because of being at HPE now, the scope of the products we have, the way we deliver systems, the scope of it is broader than what I was doing at Cray. So I've been thinking a lot about the issues of diversity in processors, diversity in how you consume or acquire computing, and the way things are changing in our world. So basically, because we're in the post-Dennard scaling era, arithmetic's not getting any faster. In fact, it's getting a little slower, but we can do more of it concurrently. And we're seeing the specialization of processors to workloads. We've seen more new architectures in processors in the past, say, 2 or 3 years than we saw, for a decade before that. Because if we can't make individual computations faster, we can combine them in ways that do specific things better. And so we see, NEC has a long vector processor, the SX Aurora. Fujitsu, the A64FX, uses an ARM instruction set with vector extensions and high bandwidth memory on the processor. Intel's got new GPUs coming. AMD has new GPUs coming, and there's just a plethora of AI chips that are specialized for different purposes. So when we started this workshop 10 years ago, it was because we were starting to see nodes that were heterogeneous. We were getting ready for systems like Titan that had a CPU and a GPU. And most of the questions we had back then were, how do I get my application to perform well on this heterogeneous architecture? And we learned a lot. And there's still a lot to be done, and there's lots of talks in the coming days of this workshop that will continue to explore that. We're also seeing challenges associated with the diversity and how that affects the system level heterogeneity and how that affects procurements and how you specify what you want. There's a tension between capacity-oriented computing and capability computing that actually increases as specialization and heterogeneity increase. So we know that for a capacity-oriented workload, lots of different jobs, small jobs, that you can improve throughput by having lots of different node types and using the best node for each job type. But we also know that if you have lots of different node types, it makes running a single capability job or a job that uses half the system or the full system, it makes it hard, it makes it unnatural, and I'd say it also makes it less valuable. And you could construct a job that does that, but it's not natural. So what do you need and how do you express that? And how do you know if you got what you wanted? There's a paper written by folks at NERSC that I was looking at this week where they developed a metric for evaluating performance in the face of heterogeneity. So they use this, different sustained performance metrics to look at the performance over time from one generation of the system to the next. And they've updated that to deal with heterogeneity, having multiple node types and assessing what's the best mix for a workload. And then there's this other heterogeneity. What about cloud? We're going to hear some talks about that later this week. We know cloud systems are really good for diversity because they can have lots of different node types. And if you're not using those weird chips, somebody else is going to pay to use them. We know that cloud is great for elasticity because there's lots of resources. And if you're not using them right now, somebody else will pay to use them. It's great for assessing the utility of new chips because you can get access to them really quickly compared to doing a competitive procurement. On the other hand, they're not architected for capability computing. And the question is, does that matter? And when does it matter and why? We know that single job performance looks pretty good at the scale used today for NWP workloads. And we're going to hear more about that this week. One of the questions I have is how many nodes of one type can you get in any one location so they're connected with low latency? I think the demand for custom supercomputers, like Cray's done for years, will continue. We're in the process of, getting the first exascale systems delivered that we have contracts for. And we've also got a bunch of orders for systems for different weather centers, and we're working on those. But what are we going to see in 10 years? What do the weather centers think they'll need in 10 years? In how to consume computing, how to purchase computing, how to decide what kind of processors you need to have. There was a really interesting paper, there's a preprint available that I learned about last week. Balaji gave a talk at the NOAA AI workshop, Climbing Down Charney's Ladder, Machine Learning in the Post-Denard Era of Computational Climate Science. And I thought this was a really interesting paper. At exascale, you still won't be able to run a global model with, say, 1 kilometer resolution fast enough for it to be your workhorse, either for forecast or science. He talks about how you can learn a lot from relatively short duration, high resolution simulations and then develop emulators. So that's the kind of work that does need a big exascale supercomputer. It's going to generate a huge amount of data, and it makes sense to do the training of emulators if you're using AI methods on the same system that the simulation runs on. So we know we've got exascale systems on the radar that they're heterogeneous. They use CPUs and GPUs, but there's an issue of heterogeneity between the software stacks for physics-based modeling and simulation and machine learning and AI. So I thought this paper was really interesting about potential new directions that we'll see the community going as a result of the end of Denard scaling and the issues getting applications to run fast enough to get the productivity you need. So this might be my last slide. I wanted to talk about, with procurement, if you need 2 or 3 or 4 different types of nodes to meet the needs of your workload and your users, how do you decide how many nodes you get of each type? So if you think of them as different partitions of the system, how many nodes should be in each? Or how much of your budget should each partition consume? And how do you predict how much AI your users are going to be doing in 4 years after you write your requirements, which is probably like 2 years into your system deployment? we know that the number of papers is increasing exponentially, but how much of the traditional modeling and simulation work will get reworked as more AI-oriented work? And then what benchmarks let you assess the performance of different specialized solutions? So that we know that there's this huge variety in chips, but how do you actually determine which ones work well for you? And what do you do if the solutions proposed by different vendors are different enough that you're essentially comparing apples and oranges? So these are things I've been thinking about. It seems like we're in a time of change with architectures, as well as how you think about specifying what you need and how you rank the possible solutions for what you need. So I'm hoping that we have discussion about this during the week. We've got I think an interesting program with people who are doing things in quite different ways. And so I wanted to just throw this out there as things to think about over the week, and I hope we can have some discussion about that. And I'm actually done.